I'm happy to come here. It's the first time for me in Scotland. I wanted to come here for a long time, actually. And so this whole first day will be mainly people from the scientific community I work in. So I tried to give like an introduction to the whole topic, also saving the other speakers some time to repeat everything. And so let's see, right. I will start with some motivation coming from, say, like engineering background. So our motivation is that we have some function f. If you want, you can always assume the dimension to be 1, but everything I write up is more or less the same in RD, at least not the problems, but at least the setup. Going into the complex numbers. And this could be interpreted as some kind of signal. It is something that we could measure, like air pressure, like sound waves, or like in medical diagnosis, like some currency measuring in the brain, like an EEG or something like this, yeah? So just some kind of signal, and then we want to it's an analog for the moment. And we want to process this. And the right space is the Hilbert space of square integral functions. So we will always assume that this integral with, let's say, the Lebesgue measure is finite. I will also assume actually that the functions are defined pointwise and they are nice. So every now and then there are some issues regarding like convergence, summability, and such stuff. There are always some function spaces which we can restrict to, such that all the things I state hold. It's not always all of L2, but usually they are dense, and then this goes through. So this is the one thing. And then what people like to do is they like to have a look at the spectrum of such a signal, which is given by the Fourier transform. And just to have the normalization, so I will take this curly or this calligraphic f of this function with the at the frequency omega is just this integral. We take the function and compare it with this, say, sinusoid or pure frequency, and that gives us the spectrum. So we have now two equivalent ways, and we'll also write that. Two equivalent ways of studying a signal. We can have a look at the temporal behavior, so we know like the signal at certain instances in time, or we can go to the spectrum and have a complete equivalent description regarding the frequency spectrum. And this is where Gabor in the 1940s saw a serious drawback already. And yeah, there it is. So this is Dennis Gabor. And in 1946, he had this paper on the theory of communication, where he said that both this temporal behavior and the frequency behavior are idealizations, and actually that in reality, like we need to process both informations almost at the same time. So you need your brain needs to process the frequencies that come from my voice to you while I speak, and you cannot wait until I have ended my sentence and then start processing. That is like the idea. And around the same time, he was also working on mathematics, on the holographic method. And for that, actually, he got the Nobel Prize in Physics in 1971. So it took 25 years from theory to the Nobel Prize, because in between the laser was invented, the laser beam in the 1960s, and only then his theory could be put into practice.
Was he located in Hungary at that time, in 46 or in?
No, he emigrated. So he was born in Budapest, in Austria-Hungary at that time. He studied in Germany, Charlottenburg University, and he had to emigrate actually to the UK because he was considered Jewish. So he emigrated in the 1930s. You can read this actually on the Nobel Prize website. Okay, and so let's have a look at this idea. So we want like a 2 or 2D-dimensional representation of a 1-dimensional or 1D-dimensional signal. And how can you do that? You do this with the so-called short-time Fourier transform. Or the engineers also called it the voice transform, which is why you will then see the letter V popping up. And for this, here we assume G to be nice. So this will be some nice function, maybe like a Gaussian or something like this. And then we take the STFT of our signal F with the window G at X and omega. This will be a point in time. This will be a point in frequency. And it's almost the same as the Fourier transform. But what we do is we window our function by multiplying it with this nice function G. So it's like cutting out pieces of your signal and then taking local Fourier transforms, and then you shift the window a bit and do the same thing again. And this can be written in the following way. I will use this notation quite often later. So this brackets, they denote the inner product on a Hilbert space, yes? So M omega TXG, these are the modulation and translation operator. So Tx of a function Gt just shifts it. And M omega multiplies it with this pure frequency. So it's a modulation. And if you would take the Fourier transform, it would shift the Fourier spectrum. Omega dot T, G of T. And yeah, so this is the inner product on this Hilbert space L2. And this dot is just the Euclidean inner product, the Euclidean scalar product of two vectors. Okay, so this, these are the fundamental operators that we use in Gabor analysis. And one fact that I state now is they don't commute in general. Often this is not a problem, but for some results I show you, they will be restricted to certain things, and the restrictions come from this non-commutativity. So what we have is, if we exchange the order, then what appears is a so-called phase factor. Okay, so we know how this is explained. Usually I will then later simply write here, this is some constant C, a unitary, it's a phase vector. Often we don't care about it, but now we know how it occurs, and we know how in principle to compute it. Okay, fine.
And they are unitary in L2.
Yes, they are unitary in L2. These operators are unitary, yes. And also the Fourier transform, as I have chosen the normalization here, is also unitary, yes. Okay, and so let's compare this with some pictures now. Just takes a moment to pop up. So here again, we have on, yeah. Okay. Here we have our signal. It's a very simple artificial signal I made up. Maybe the okay, so on the left side, you see this signal. It's like made up of two cosine, it's the real part, so it's like an addition of two cosine functions with different frequencies, then one cosine function, and then like a cosine function where the argument increases over time. And okay, so there is a little bit annoying, but this is that's a bit noisy, yes. Okay,
It's not good.
and so for the moment, I will just do it like this. So here on the left-hand side, you see the same signal multiplied with like a Gaussian function. And then we take this short-time Fourier transform at x omega. Okay, since it's a complex valued functions, we took the absolute values. And then what you can see is something like a musical score. So it really tells you at what time which frequencies occur. And as said, this is a very simple signal. But
Yes, it's flickering. I think
yes,
it's because of the adapter.
okay. So you have seen now the picture, and yeah, so the idea is to have something like a musical score. Okay, so for the moment, I'm done with the pictures, so I'm going back to the blackboard. But that is like this idea of the short-term Fourier transform, and you can somehow see how it's a bit superior to the ordinary Fourier transform, because you have some local time frequency behavior in a joint representation. So what I'm writing up now are some minor, well, not minor, some important facts. I will not prove many of them, but I will start with the fundamental identity of time frequency analysis. Just to give you a feeling how one can work with these operators and how many theorems are proved with maybe longer computations, but these are like the basic things you need to know. So you take the definition. Okay, what is next? Next, we know, for example, that the Fourier transform is unitary. So we have Parseval's identity. We can take the Fourier transform of both here, and the inner product does not change. Next, you need to know how the Fourier transform interacts with modulations and translations. They are exchanged more or less. And what you get is you get a translation by omega, a modulation by minus x, and then the Fourier transform of G. Now we swap them. And at the cost of a phase factor, which I pull out. So we have some phase factor, ff, and m minus x t omega fg. And this is the same as up to a phase factor having the short-time Fourier transform of the spectrum with the Fourier transform of the window at omega and minus x. So this is called the fundamental identity of time frequency analysis. And we have a couple of interpretations for this. So first, as you can see, the coordinates, they don't only get swapped, but it's more or less a rotation of the vector x omega by 90 degrees. And so if we take the Fourier transform, apply it again, usually you get back the function flipped. But actually what you do is you don't flip it, but you rotate the time frequency plane by 180 degrees. And if you apply the Fourier transform 4 times, then you do a full rotation and you end up with your original function. And also, what you can see, if you localize f with some window g, then as said, the spectrum will be localized with the Fourier transform of g. So there is this trade-off and the uncertainty principles. So if G is smooth, then G hat will have rapid decay and vice versa. And usually you want nice decay and good localization. And due to uncertainty principles, this is only possible up to a certain uncertainty. So an ideal time frequency representation is in principle not possible. You always have, like, you can find some band in which you know your function, and then you have some other band in which you know the spectrum. And if you go to the Dirac delta, so you could actually put a Dirac delta here, but then this would give you the constant one function and you would have no localization in the distributional sense. And of course, we want to know, can we get our function back from the short-term Fourier transform? And the answer is yes. So assume you have, like, say, 2 windows which are not orthogonal. Then you can actually write f as 1 over this inner product of these 2 functions. And then you take this double integral, you take the VGF, and then you take the modulations, translations of this function G tilde. And so it's, in a sense, quite similar to the Fourier inversion formula. And in particular, you can pick G tilde to be the same as G. You can normalize it, and then you can forget about this factor here, and here you have the same thing. Yes. What we see is we have, like, an integral representation of this function on the Hilbert space of square integrable functions. This contains highly redundant information. It's a separable Hilbert space. So what we want is a series representation instead of an integral representation. And so our goal is to write f as a sum where lambda is some discrete index set. Usually I take it to be a lattice. You can just take, if you want, set 2D. We want some coefficients, and I will now use this notation pi lambda g, where pi lambda is just a short notation for combining the translation and modulation. And we'll always identify this as R2. So this is then called the time frequency plane. In quantum mechanics, you have similar principles. You don't have time and frequency, you have position and momentum. And then this would be called the phase space. Okay, so this is what we want. And then, of course, questions pop up. First of all, can we find, say, coefficients which are in L2? Maybe, maybe not. And we could also ask, when does this sequence determine? Of course, we don't want that one sequence of coefficients could give you 2 different functions, right? And all this.
That C lambda, there is no goal of VGF, the short-term Fourier transform?
At the moment, not. I will relate it to the short-term Fourier transform, but at the moment, it's just some sequence of coefficients, yeah. And we'll need to clean the blackboard at some point now. So these are like typical questions that pop up, and like when is this series then convergent and so on. And the right setup is then to go into the area of frames. So frames are just a generalization of the concept of a basis. The vectors need not be orthogonal, and it can be an overcomplete system. So you can have more vectors than you would really need to generate the space. So we say that I have not introduced this notion yet, right? So this is a Gabor system. So it's the collection of the time frequency shifts of the function with respect to this index set. This is a frame for our Hilbert space. So I'm always taking here L2 of RD, but the concept is also for more abstract Hilbert spaces, also for finite dimensional ones. If and only if there exist constants A, B, positive and finite, such that we have the following energy equivalence, one could say. So L2 norm of the function bounds the small L2 norm of the sequence of coefficients which I obtain from taking these inner products of f with the Gabor system. And this is also bounded above by the norm of the function. And this needs to hold for all there. Then we say this is a frame. And then we know, okay, these coefficients are square integrable. They uniquely determine our function. However, for one function, we may have more than one way of representing it, because in general, the system is redundant. And so there are more ways to obtain coefficients. But yeah, if you take here f minus g, since this will not vanish, the function cannot vanish, and so we have that the two functions can be distinguished from the samples. You don't agree?
We would use G for that explanation.
Okay.
That confused me for.
Okay, sorry. Yeah. So this inequality, we are almost arriving at the matrix now. There is an operator associated to a Gabor system, which is the frame operator. So SG acting on F. So we can also like write the dependence on G and lambda, or usually the window is fixed and then we only write lambda. And this is now basically the same thing as here, but now the coefficients really come from the STFT. So in general, this will not be F. If you have an orthonormal basis, then the frame operator is the identity, then you have it. If it's a tight frame, so if A equals B, then you have a multiple of the identity operator. But in general, what comes out will be a bit different from what you put in. But then the frame inequality, because you can identify this, that this middle expression, the frame operator applied to F, then taken into the inner product with F. So you have the spectral bounds of this operator. It's invertible. And then you have that if you have a lattice, it also commutes with time frequency shifts. And then actually you can write F, for example, by taking the coefficients with the Gabor system and taking the synthesis with the so-called canonical dual. You could also have G here and S to the -1 G inside if you prefer. So this operator is actually a composition of two processes. What we do is we first analyze our signal. So we take these inner products and then we synthesize these inner products to get a new function. And so we call C. So this can also have an index like lambda or G or whatever, but I just write C. This goes from this Hilbert space of signals into the Hilbert space of coefficients by mapping the signal to these inner products. And then there is the adjoint operation, the synthesis operation, going in the other direction. And there you take a sequence and you make a function out of it. Always with respect to this Gabor system. And in this way, we actually have that S is a composition of these two operations. One is the adjoint of the other, so S is self-adjoint. And this is where a duality concept already comes in. So we have a complementary concept of Rees sequences, so complementary to Gabor frames. And in principle, what we do is this frame inequality. So we had the L2 norm, so the big L2 norm outside and the small L2 norm inside. We can swap this and then we speak about Rees sequences. So G, the Gabor system with window G and lattice lambda or index at lambda is a Rees sequence. If and only if there exist again these constants that A, and now we have, I will not, because it might be confused with the phase vector otherwise if I just write this little L2 norm is bounded now by the capital L2 norm if we synthesize these coefficients to be a function. C lambda. Pi lambda G. There. These concepts are more or less dual to each other in the sense I will describe now. So the so-called duality theorem, I will first state it and then explain the things that pop up there. So the following things are equivalent. This system is a frame. Is equivalent that the system over the adjoint or symplectic dual lattice is a Rees sequence. So now we need to explain what the adjoint or symplectic dual lattice means. It's a rotated version of the classical dual lattice. And the reason why it is more important than the dual lattice in time frequency analysis is because it's described by means of commuting time frequency shifts. So these are all points in the time frequency plane, such that the time frequency shift with lambda circle commutes with all the time frequency shifts of the original lattice. So now lambda is really a lattice. And for that, recall, a lattice is just the image of the integers under an invertible matrix. And a priori, this is only a set, but it turns out it also has a group structure, and it is indeed a lattice, and we can characterize it in the following simple way. We take the inverse transpose of this matrix and then rotate by 90 degrees. So this is the matrix, the standard symplectic matrix, J, and these are blocks of size D times D. So identity, identity, and zeros everywhere else. Okay, so it's, if this J would not be there, it would be the standard dual lattice, but in time frequency analysis, we like this better because of these commutation relations.
Isn't lambda 0 stable under rescaling by real numbers?
Well, lambdas, you can rescale lambda, then also lambda 0 is scaled.
This lambda, the set you, the formula you described, doesn't that, if I can just multiply both sides by √2, it still stays the same, right?
If I multiply one by, say, 2, then the other is multiplied by 1/2. Because you have the inverse transpose here. So what we have is, okay, let's say the volume, or actually it's the co-volume of lambda in R2D, but I will simply write volume lambda. It's like the determinant of M in absolute values. And so the volume of lambda 0 is determinant to the -1.
I was asking about the formula for the definition of lambda 0.
Yeah.
Inside the set.
Yes.
I can rescale both sides by an irrational number.
No. The thing is, are they still here? No, they are gone. We had this commutation relation. Where this exponential factor pops up. And that happens if we interchange this translation and modulation. And since they define the time frequency shifts, if you swap them, you also need to swap translations and modulations, and then these phase factors will play a role, actually. And so you cannot simply rescale as you wish.
So it is a lattice.
Yes.
Just checking.
Yes. If you want, an equivalent definition is that the symplectic form is an integer for all lambda in lambda. And this symplectic form, I would have defined it later, but I can also define it now, is more or less it's skew symmetric, so it's not the standard inner product, Euclidean inner product, but where you put this matrix J in between. So as you know it from symplectic geometry or maybe Hamiltonian mechanics, or maybe you have not seen it, but yeah, it's just, you know, twisting a bit this Euclidean inner product. Okay. And okay, we started with this whole duality theorem. Because I want to arrive at something like a matrix. Actually, I want to arrive at the Laurent operator on the Hilbert space of sequences. And this is now done by switching the order of the coefficient and synthesis operator. So we go from L to little l from sequences to sequences. And this operator, I will denote it by T. Maybe not so good because it's also translation, but I did it like this. I will stick with it. Is now simply this, and what it does. So we call it the Gramian of this Gabor system, and it has the following structure. So T acts on sequences, and so it has almost a matrix structure, but cross by infinite, and looks like this. So we again have time frequency shifts by one index, and take the inner product time frequency shifts with some other index. And this gives us a bi-infinite matrix, and this has some structure. But as time frequency shifts do not commute in general, it might not always have a very simple structure. It's always a nice structure. It's always a block Laurent structure, but not always a Laurent structure, which is where I want to arrive for the following reason. So we have the following operator inequalities. So the identity on the sequence space is, if we normalize it by the volume of the lattice, then we have this operator inequality for the Gramian. And this is equivalent that the Gabor system is a frame in the, and we can also write this as an operator inequality. So identity here on the function space. And the constants are the same on both sides. That is the point which is most important for where my research then starts. Let's backward. And as I already said, this has a block Laurent structure. And for Laurent operators, there is a theorem that you can compute the spectral bounds by a Fourier series. So let me just recall, or maybe for myself. Let's denote it by L. It acts on the sequence space. And then this operator is constant on the diagonal. In the other direction. And then we can build the Fourier series. Where we take the coefficients to be the entries from the diagonals. And then, now assuming that this sequence is nice enough, and since it comes from the Gabor system, assuming that the function G is nice enough, we can bound, but we don't bound. We have that the operator norm So here now of L, we are still, it's just for indexing reasons, I cannot draw it for set 2. But of course, for Gabor systems, we always have here set 2D. In the operator norm, so from L2 to L2, this is, let's write the max. Actually, it should be the essential supremum, but let's not care about the technicalities of this Fourier series. And the inverse operator, we take the inverse operator norm of this, is actually the essential infimum. I will just write minimum of this Fourier series.
In the general case, absolutely equivalent. Yeah. Complex. Positive.
I don't think so.
Your L is. Yes, it's alpha joint or whatever.
Yeah, okay, yeah, there are some assumptions which I hide, yes.
One positive definite.
Yes, okay. Okay. Okay, I was looking at this from the Gabor viewpoint with the self-adjoint operator and the nice function in the background. But otherwise you would say here absolute values, yeah, okay. Yes. Okay, for whatever comes after, I don't need them, so I didn't put them here in. Thanks for pointing this out, yes. So we have the following proposition. Due to Janssen. And now we consider again our Gabor system. And then we have if this volume is 1 over 2n, and n is a natural number. So we have 2n points per unit square. So we would say the density is an even density. Then A is now the minimum, or actually again the essential infimum over the following Fourier-like series. We take this volume lambda to the -1. We sum over the adjoint lattice. So we are using basically this proposition down here. So if we and this duality theorem. So if we have a Gabor system which is a frame, then the adjoint system, so over the adjoint lattice, is a Riesz sequence, and for this we have the Laurent operator structure, and now we use this fact that you can build a Fourier series, and that Fourier series gives you the exact spectral bounds. And here we have, yeah, I used this so we can write VGG. So we take this voice transform sampled on the adjoint lattice. And here we take e to the 2 pi I. And this standard symplectic form between the vectors. I mean, it doesn't change the minimum, it only changes the location of the minimum because it rotates it. And B is the same thing, but with the maximum. And here, okay, I again don't put these absolute values because now I assume that G is usually a Gaussian or something. Then it's really not necessary. And I think also for the Hermite functions, which I will present, it's not necessary. Okay, so this was like the theory part, which I wanted to build up. I only took like 5 minutes longer for it than I wanted. Are there any questions at the moment regarding?
Do the asymptotics of the determinants of the final truncation have a meaning? Because this is a complex matrix, and usually that's something to look at.
Yes. cannot answer it right away, but
Yeah,
I mean, if you have some decay, from
yes,
the
and,
off
the
diagonals,
asymptotics tell you about
then
the
it
spectrum.
tells you something about the spectrum. Yeah, yes.
Is that one standard thing to
Yeah,
do
yeah,
when
yeah.
you have a Toeplitz matrix.
Yes, and that's also the usual way. If you want to know whether a Gabor system is a frame or not, you have a look at matrix like this, and then you see, okay, it's diagonal dominant. You can bound the off diagonals by something very small, for example, and then you can say, okay, you have a frame or you don't. Other questions? Yes.
You always consider inverses. Lambda inverse. What happens in this?
Not lambda inverse. It's just so the volume it's a number, and so this is just 1 over.
And M inverse. There was also.
Yeah, here. So M is a matrix, and this is the inverse matrix transposed. So this is M minus T is just short notation for the inverse matrix.
And M itself.
M itself is some invertible matrix.
Thank you.
Okay, and now let's see whether. So now I will present some more recent results which I obtained with my colleagues. For that, because I thought time will be short already at this point, I prepared some slides. And I will start with, maybe one thing is that there is some space here. I should say what the frame set is, because we were talking about the frame set problem. So let's denote it by something like this. So we fix some window function G, and the frame set contains all index sets such that this Gabor system is a frame. Okay. For example, the necessary density condition is that the volume of the lattice cannot be greater than 1. You need at least 1 sample per unit square to know your function. Otherwise, you have too little information. And under very mild assumptions on your window G, so for example, this already holds for the head function, you must have strictly greater than 1. So you must have oversampling. You cannot have a basis with these functions. And this is why we study frames in the first way, because we want the nice time frequency localization, but with this you cannot have a basis. You need to be redundant. And then you study frames. And then there are all kinds of questions like, what is the frame set of a function? And this is really very complicated in general. And let's start with the frame set of Hermite functions. So this is just this capital Hn at the very end of the equation is a Hermite polynomial. So these are orthogonal polynomials, and we multiply them with a Gaussian function. And we normalize them such that they have unit norm. Okay, here's like how you can generate them by differentiating a Gaussian. But basically, you have very nice polynomials multiplied with a Gaussian, and here you see the first 4 Hermite functions where we always start with index 0, which is the Gaussian function itself. And for that, we want to know, okay, what is the frame set? And this is quite tricky, actually. So what we know is that for the Gaussian, this is a frame if and only if the lattice has density greater than 1. This is a famous result in time frequency analysis from 1992 due to Jura Liobarski, Christian Seib, and another paper of Christian Seib and Robert Wallstein. For the first Hermite function. And here now we have to restrict So this already to rectangular lattices. So for general lattices, we don't know. And we only know the direction. That if the density is strictly greater than 2, then this is a frame. So more generally, this holds for the nth Hermite function and m+1. This is a result due to Karl-Heinz Gröchenig and Jurel Lyubarski from 2007. And what we also have is that this, so we take the square lattice, let's write it like this, is not a frame. Or, okay, 0 is also included. 1, 2, and 3. 1 is due to Lyubarski and his former student Nees. 2 and 3 is due to Jakob Lembig. And then what we showed, with Shakulovska and Slotnikov, still under review, is that the system GHN then 1 over square root n+1 set to is actually a frame as soon as n is larger than 4. This was very surprising to us. We wanted to prove the opposite actually. And we tried for some time to prove the opposite for n equals 4 and couldn't make it, and we couldn't make it for n equals 5. And so we thought, okay, maybe we are trying to prove the wrong thing. And yeah, it turned out the opposite is correct. And here is a short sketch of the proof. So what we use is the following criterion. A simple calculation. Due to time restrictions, I will not carry it out, but the manipulations you need are as simple as the ones I did in the beginning. Plus, in between, you need the Poisson summation formula, the triangle inequality, and Cauchy-Schwarz inequality. So it's all quite basic, but it's quite long to write up, and so I will save us the time. So what we have is that this middle part in the frame inequality so what you do is you write this as inner product and the same thing complex conjugate. Then you use Poisson summation formula, which makes 1F and 1G swap places. Then you take the triangle inequality, Cauchy-Schwarz, and you end up that this is bounded by volume lambda to the -1 sum over the adjoint lattice. This is the part from the Poisson summation formula. Absolute value VGG evaluated on the adjoint lattice. This is the part with the triangle inequality. Norm F squared, and this is Cauchy-Schwarz, that actually VGG at 0 dominates VGG everywhere else. And so what we see is this guy here is an upper frame bound. It's not necessarily the best possible, but it's an upper frame bound. And what we have is if B tilde is strictly less than 2, then this is a frame, because what you do is you subtract the frame operator, like in this representation, which is again a duality theory due to Janssen, similar to what I've shown you with the Riesz sequences. You compare it to the identity, VGG at 0, so a time frequency shift with 0 is the identity operator. So this cancels and you're left actually with this sum without the origin. And if this is less than 1, then you can, by using a Neumann series argument, say that your operator is invertible. And this is what we then prove. This is what you see here. I mean, this is just, of course, the numerics. We did a rigorous proof for this. And this is how you, the behavior of this B tilde, which is a quite curious thing. So at first we expected some monotonicity and thought this would be some nice and easy proof, but it wasn't. And the difficulty is if you pick G to be a Hermite function, then this STFT contains some Laguerre polynomials times a Gaussian, and then understanding the zeros, so the distribution of the zeros of Laguerre polynomials is the hard thing to do. That's really not so easy. And okay, we also did some more stuff. Then just for fun, we picked the 15th Hermite function, for example, and had a look how much can this criterion give us, for example, for square lattices. And actually we could prove already from 11 on and not only 16 on, we have a frame, so the density can be much less than set by this sufficiency criterion. And what you see here in green is what was known due to Kröchenik and Lyubarsky. And what you see here is what you get numerically with this method of comparing the frame operator to the identity and seeing whether this is good enough or not. But there are many other criteria which actually give you much more. But this was actually the first result, positive result. There were lots of no-go results, so you don't have a frame if you have something like this. This was the first result in the direction that you actually have a frame. And just to show you, okay, these are the two postdocs with whom I worked. It's on the archive if you're interested. And I will only mention the next result because the time is up. The next result I would have talked about, and we can, if you are interested, discuss in a break or on Friday, is with Laurent Béthomin and Stefan Steinerberger, where we picked up a question on optimal condition numbers. So we had this frame inequality, and for numerical algorithms to be stable, you want that the ratio B over A, so the condition number of that matrix, is small. And if you fix like the volume of the lattice, so you fix the computational cost, because otherwise it would be unfair. If you have way more information, of course, you are performing better. But with like having the same amount of information, what is the best lattice that you can pick? And there was this conjecture due to Thomas Stromer from 2003 that since if you take the Gaussian and VGG with the Gaussian is a radial symmetric function, it's actually a Gaussian, that sphere packings should play a role and that the hexagonal lattice should minimize this condition number. He was not completely wrong, but the part that was missing is like the upper frame bound corresponds to sphere packing, the lower frame bound to sphere covering. And in dimension 2, because geometry is restricted, it happens that the hexagonal lattice solves sphere packing and sphere covering in an optimal way. And that was how we approached the problem then. And we could show indeed, okay, B is minimized for the hexagonal lattice, A is maximized, and so it implies that the condition number is minimized as well. And yeah, I mean, you see, it's a very long paper, 62 pages. We have a lot of results. There are 3 or 4 more results in very different fields. If you read the first 5 pages, you're done with the paper. If you read until page 16, you also have the proof sketch, and the other 40 pages are only the technical details. Okay, and now my time is really up. And here. So thank you for your attention.